So let's talk about something huge that's happening right now in the tech world. We're witnessing a fundamental shift where firmware engineers, the people who work deep in the hardware, are evolving. They're going from managing bits and bytes to architecting the intelligence that's literally going to shape our physical world. Let's dive right in. And really, this quote right here, it says it all. For the longest time, the AI conversation was all about the cloud, about massive data centers. But that's changing. As Forbes put it, AI's center of gravity has crashed down to the bedrock of the physical world. We're talking about the devices in your hand, in your car, in your home. This isn't just a minor update, it's a full-blown revolution. So our story really kicks off with AI leaving the nest, leaving its home in the cloud. We're shifting away from what you could call the generative hype era, where AI was this cool browser-based novelty. Now we're entering the age of physical utility, where AI is a real workhorse, doing critical jobs in our factories, our homes, and our hospitals. And this really breaks down that shift, doesn't it? In the past, it was all cloud-based, driven by novelty. But now, we're talking about physical AI that runs on the edge. It's not about being clever, it's about being trustworthy. It's not centered on a browser, it's centered on the physical environment it operates in. It's a whole new way of thinking. And look, if you're a firmware engineer, this is the part where you should really lean in. Your job description has been completely rewritten. It's not just about flipping bits in a register anymore. The new game is about architecting these complex, sophisticated systems that blend the device and the cloud. You have to make them fast, efficient, and secure. You're not just a coder. You are now an AI architect. Okay, so if we're saying you're the new architect, what's in your toolbox? What do you need to know? Well, this next part is all about the seriously powerful new hardware and the absolutely essential software skills you're going to have to master to build this future. First up, the hardware, the very foundation we build on, yeah, it's completely different now. There's this huge trend called component collapse. Instead of a big circuit board cluttered with dozens of different chips, we now have these incredibly powerful AI-native systems on a chip. Think about something like the NXP IMX93W. It's got your main CPUs, a real-time controller, and a neural processing unit, a specialized AI brain, all squeezed onto one tiny piece of silicon. It's doing the job of what used to take 60 separate parts. And just look at the sheer range of silicon we're talking about now. On one end, you have super efficient chips, like that NXP one, perfect for a smart thermostat. But then, look in the middle. The MediaTek Genio Pro. Its NPU is pushing over 50 TOPS. That's 50 times trillion operations per second. That's enough horsepower to run a large language model right there on a robot. No internet connection required. That's a game changer. So, you've got these tiny power-sipping devices. How in the world do you run sophisticated AI on them? The answer is a field called TinyML. And it's exactly what it sounds like. It's the art of taking these massive machine learning models and shrinking them down, sometimes 1,000 times smaller, so they can fit on a tiny microcontroller that uses less than a milliwatt of power. We're talking about intelligence that can run for years on a little coin cell battery. Okay, so how do you actually pull off that magic trick? How do you shrink a model by 1,000 times? Well, it's a three-step process. First, there's quantization, where you basically make the numbers inside the model less precise but way smaller. Then you do pruning, where you surgically snip out the parts of the model's brain that aren't pulling their weight. And finally, there's distillation, where you use a big, smart teacher model to train up a tiny little student model to be just as good. Mastering these three is absolutely key. All right, but it's not all smooth sailing. This journey comes with its own set of trials. Think of them as 4 dragons that every new AI architect has to face. Slaying these dragons, that's the real test. First up, the bricking threat. And this is a nightmare scenario, right? Imagine you push out a software update to thousands of devices in the field, say remote medical sensors, and something goes wrong. You've just turned them all into useless plastic bricks. It's a catastrophe. That's why having bulletproof update strategies like A/B partitioning that lets you roll back safely aren't just a nice-to-have anymore, they are mission critical. Next dragon, the memory crisis. And just look at this number. Plus 246%. That's the year-over-year price hike for the kind of memory we use in these devices. Why? Because the same AI boom that's fueling data centers is sucking up all the global supply, creating a massive shortage for us at the edge. It puts insane pressure on your costs. And this chart, it really drives the point home. Forget the other bars for a second. Just look at the far right. That's our world. This kind of price pressure forces you, the architect, to make tough choices. You have to use smaller models, and you have to start thinking about things like flashware, the idea that updating your device too many times can literally wear out its memory. Dragon number 3 is a fight against physics itself, the cooling crisis. We're packing an insane amount of computing power into these tiny, sealed boxes with no fans. These chips get incredibly hot, and honestly, we're hitting the absolute physical limit of what we can cool passively. Heat is no longer an afterthought, it's a primary design constraint. And believe me, the cost of ignoring that heat is huge. When a chip gets too hot, it throttles itself, and your performance can get slashed by up to 50%. Even worse, it kills the device. For every 10 degrees Celsius hotter it runs, you cut its lifespan in half. So managing heat isn't just about performance, it's about whether your product survives it all. And that brings us to our final dragon, the RTOS paradox. Think about it like this. You've got two things that just do not want to mix, like oil and water. The water is your real-time control loop, say for a drone's motors. It needs perfect, predictable timing. The oil is your AI task, like object recognition. It's greedy, unpredictable, and comes in bursts. The real-time operating system, the RTOS, has to somehow act as an emulsifier and get them to play nice without the whole thing crashing. So how do you solve that? Which emulsifier do you pick? Well, it's not a one-size-fits-all answer. For simpler stuff, you might go with the old reliable, free RTOS. If you're wrestling with a really complex multi-core chip, maybe Zephyr is your answer. But if you're building a car or a medical device, something where failure is not an option, you're looking at something like ThreadX, which is built for that kind of safety-critical work. Okay, you've faced the dragons, you've survived, but now you enter a totally new landscape, one that's governed by some very strict new rules. Security isn't just a feature you bolt on at the end anymore. It's a legal requirement. If you're selling a product in the EU, this right here, the Cyber Resilience Act, it's your new reality. And these aren't suggestions. This is the law. You have 24 hours to report a hack, you have to maintain a detailed list of every piece of software on your device, and you have to provide security updates for at least 5 years, for free. Let's be clear, the legal liability has shifted squarely onto the shoulders of the engineers and the company. And if you're wondering why all these rules are suddenly so strict, well, it's because of this number. Over 820,000. That's how many automated attacks are hammering away at internet-connected devices every single day. The threat isn't just real, it's relentless. And that's why security has to be priority number 1, right from the start. So, let's bring it all together. You've mastered the tools, you've slain the dragons, you've learned the new rules. What happens next? A total transformation. This is where the firmware engineer is truly forged into something new, the AI architect. And a huge part of that change is how we think about safety. Get this, 70 to 80% of all critical security bugs in C and C++ code are simple memory errors. This has been the Achilles heel of embedded systems for decades. But now, especially for these complex AI systems, there's a new solution gaining incredible traction, the programming language Rust. I mean, the numbers really do speak for themselves here. The risk of those memory bugs just drops off a cliff with Rust. Why? Because the language itself has safety rules built in that prevent you from making those mistakes in the first place. In the high-stakes world of physical AI, where a software bug can cause real-world harm, that kind of guaranteed safety is becoming an absolute must.
So here we are. The transformation is complete. The engineers who build the bedrock of our world are no longer just writing code. They are architects, designing and building autonomous, intelligent systems that will live and work alongside us. Which brings us to one final, crucial question. With this newfound power to shape the world, are they ready for the immense responsibility that comes with it? Well, that's something we're all about to find out together.